Proxima Centauri, the closest star to our solar system, has long been a subject of fascination for astronomers. This small red dwarf, discovered in 1915 by Scottish astronomer Robert Innes, is part of the Alpha Centauri system, which also includes Alpha Centauri A and B. Despite its proximity, just 4.24 light-years away, it remains invisible to the naked eye due to its relatively low brightness. However, Proxima Centauri holds immense scientific value, especially as the host star of Proxima b, an exoplanet that orbits within the star's habitable zone. Red dwarfs like Proxima Centauri are smaller, cooler, and much longer-lived than stars like our Sun. Their low luminosity makes them challenging to observe, but it also means that their habitable zones are much closer to the star. For Proxima, this translates to an orbital distance of just 0.05 astronomical units, a mere fraction of the distance between Earth and the Sun. This close proximity exposes Proxima b to intense stellar activity, including frequent solar flares and high levels of radiation, making its environment starkly different from Earth's. The discovery of Proxima b was a monumental achievement in exoplanet research. Using the radial velocity method, astronomers detected subtle wobbles in Proxima Centauri's position caused by the gravitational pull of an orbiting planet. These wobbles allowed scientists to estimate the planet's mass and orbital period. In 2016, the European Southern Observatory officially confirmed the existence of Proxima b, marking a breakthrough in the search for potentially habitable worlds beyond our solar system. While ground-based observations have provided valuable insights into Proxima b, they come with significant limitations. Atmospheric distortion and light interference hinder the ability of Earth-based telescopes to capture detailed data about the planet's surface or atmosphere. Most of the information we have, such as its mass, distance from the star, and orbital characteristics, relies on indirect measurements. To uncover deeper truths about Proxima b's environment and its potential for life, more advanced observational tools like the James Webb Space Telescope, JWST, are indispensable. Proxima Centauri's role as a gateway to understanding exoplanetary systems cannot be overstated. As the closest star system to Earth, it offers a unique opportunity to study the conditions necessary for life. Proxima b, in particular, represents a tantalizing possibility. A rocky, Earth-sized planet with the potential to harbor water and maybe even life. However, the challenges posed by its harsh environment make it a complex puzzle for scientists to solve. The James Webb Space Telescope, JWST, is not just another tool in the arsenal of astronomy. It is a revolution. Designed as the successor to the Hubble Space Telescope, JWST was envisioned to address the limitations of its predecessor and push the boundaries of human knowledge. While Hubble has provided invaluable insights into the cosmos, including the age of the universe and the discovery of thousands of galaxies, its capabilities are constrained by its focus on visible and ultraviolet light. JWST, by contrast, is built to observe the universe in infrared wavelengths, allowing it to peer through cosmic dust and uncover phenomena invisible to Hubble. One of the key design features of JWST is its primary mirror, which spans a staggering 6.5 meters in diameter, more than double the size of Hubble's mirror. This larger mirror enables JWST to collect far more light, making it capable of observing extremely faint and distant objects. Coated with a thin layer of gold to enhance its infrared reflectivity, the mirror is composed of 18 hexagonal segments that work together to create a highly sensitive observational platform. Another groundbreaking innovation is JWST's 5-layer sunshield, which keeps the telescope's instruments at a constant temperature of about -233 degrees Celsius. This ultra-cold environment is crucial for detecting faint infrared signals without interference from the telescope's own heat. Each layer of the sunshield is made of a specialized material called capton, coated with aluminum to reflect sunlight. Unlike Hubble, which orbits Earth, JWST operates from the second Lagrange point, L2, a stable position approximately 1.5 million kilometers from our planet. This location minimizes interference from Earth's heat and light, allowing JWST to maintain continuous observations. The telescope can study everything from the earliest galaxies to the atmospheres of exoplanets like Proxima b. Its focus on infrared light is particularly significant as it allows astronomers to study phenomena that are redshifted, objects whose light has been stretched to longer wavelengths as the universe expands. JWST's capabilities extend far beyond mere observation. It is designed to answer some of the most profound questions in science, including the origins of galaxies, the formation of stars, and the conditions that might support life on other planets. With its state-of-the-art instruments, including the Near-Infrared Camera, NIR-CAM, the Infrared Instrument MIRI, and the Near-Infrared Spectrograph, NIR-SPEC, JWST is not just a telescope. It is a time machine, a laboratory, and a beacon of human ingenuity. Proxima b has captivated scientists and the public alike as a potential second Earth. Situated within the habitable zone of its star, the planet has the right conditions to potentially support liquid water, a key ingredient for life as we know it. With a mass roughly 1.17 times that of Earth, Proxima b is likely a rocky planet, similar in composition to our own. Its proximity to Earth, just over 4 light-years away, makes it an ideal target for studying the potential for life beyond our solar system. However, Proxima b is far from a perfect twin of Earth. One of its most striking features is that it is tidally locked, meaning one side of the planet is in perpetual daylight while the other is in eternal darkness. This creates a unique environment with extreme temperature differences between the two hemispheres. The region where day meets night, known as the Terminator line, may offer a narrow twilight zone with conditions moderate enough to support life. The challenges posed by Proxima b's environment are significant. Its host star, Proxima Centauri, is a red dwarf known for its intense solar flares, which can emit bursts of X-rays and ultraviolet radiation. These flares could strip away the planet's atmosphere over time, exposing its surface to the harshness of space. If Proxima b retains any atmosphere, it likely requires a strong magnetic field to shield it from radiation. Without such protection, the surface environment would be hostile to life as we know it. Despite these challenges, scientists are optimistic about the potential for life on Proxima b. The planet's position within the habitable zone suggests that liquid water could exist either on its surface or in subsurface reservoirs. Life might adapt to the harsh conditions much like extremophiles on Earth, organisms that thrive in extreme environments, such as deep-sea hydrothermal vents or high-radiation zones. These adaptations could include radiation resistance, subsurface habitats, or unique biochemical processes. The search for life on Proxima b is more than just a scientific endeavor. It is a quest to answer one of humanity's oldest questions. Are we alone in the universe? Proxima b represents a tantalizing possibility, a rocky, Earth-like world that might harbor the conditions necessary for life. As our technology advances, so too does our ability to explore this intriguing planet and uncover its secrets. While Proxima b presents tantalizing possibilities, its environment is profoundly influenced by the nature of its host star, Proxima Centauri. Unlike our Sun, Proxima Centauri is a red dwarf star, smaller, cooler, and significantly less luminous. Its reduced size and temperature mean that its habitable zone is much closer, pulling Proxima b into an orbit just 0.05 astronomical units from the star. About 20 times closer than Earth is to the Sun. This proximity creates a unique set of challenges for the planet and any potential life it might host. One major issue is Proxima Centauri's stellar activity, particularly its intense and frequent solar flares. These flares are powerful eruptions of energy that release high doses of X-rays and ultraviolet radiation. Such events are far more common and energetic in red dwarfs than in stars like our Sun. For Proxima b, this means a constant bombardment of high-energy particles, which could strip away the planet's atmosphere over time. Without a protective magnetic field like Earth's magnetosphere, any atmosphere on Proxima b would be vulnerable to erosion, leaving its surface exposed to harsh radiation. Even if Proxima b retains some of its atmosphere, the radiation from Proxima Centauri poses serious challenges to life. High levels of ultraviolet radiation can break molecular bonds, preventing the formation of complex organic compounds. This would severely limit the potential for life to develop or sustain itself on the planet's surface. On Earth, organisms like Deinococcus radiodurans have evolved mechanisms to repair DNA damage caused by radiation, suggesting that life on Proxima b might similarly adapt. However, the level of radiation resistance required would be extreme, possibly necessitating entirely new biochemistries. Interestingly, Proxima b's tidally locked nature may offer some protection. While one hemisphere faces constant radiation from Proxima Centauri, the planet's dark side could serve as a refuge. Subsurface habitats or deep caves could shield potential life forms from the worst of the radiation. Similarly, if Proxima b has subsurface oceans, they could provide a stable, radiation-free environment where microbial life might thrive, much like the ecosystems around hydrothermal vents on Earth. Despite these challenges, scientists remain hopeful that Proxima b's extreme environment provides a unique opportunity to study the adaptability of life. By observing how organisms might survive or even thrive under such conditions, researchers can expand their understanding of what makes a planet habitable. Proxima b is not just a potential home for life. It is a natural laboratory for testing the limits of life itself. The planet's proximity to Earth and its position within the habitable zone of its star make Proxima b one of the most exciting exoplanets in the search for life beyond our solar system. However, the extreme conditions created by Proxima Centauri's stellar activity pose significant obstacles for any potential life on the planet. Studying Proxima b with advanced telescopes like the James Webb Space Telescope will be crucial in answering some of the most profound questions in science. Questions about the nature of life, the habitability of exoplanets, and the future of exploration beyond our solar system. Proxima Centauri and its exoplanet, Proxima b, represent both the promise and the challenge of exoplanetary exploration. While Proxima b's Earth-like features spark excitement, its hostile environment and the effects of its parent star will require ingenuity and technological advancement to fully understand. The James Webb Space Telescope and future missions will play a crucial role in unraveling the mysteries of this intriguing world, bringing us one step closer to answering the age-old question: are we alone? As we continue to explore the possibility of life beyond our solar system, Proxima b stands as one of the most promising targets for future research. Situated just over 4 light-years from Earth, it offers a unique opportunity to study a potentially habitable exoplanet in an environment that is much closer than other exoplanets currently under investigation. While its proximity makes it an attractive candidate, there are still many unanswered questions that researchers must grapple with before concluding whether Proxima b could actually support life. The key challenge in understanding Proxima b's potential for habitability lies in the nature of its host star, Proxima Centauri. Unlike the Sun, which has a relatively stable output of energy, Proxima Centauri is an active red dwarf star that is prone to emitting powerful solar flares and bursts of radiation. These stellar flares, which occur much more frequently than those of our Sun, have the potential to alter the conditions on Proxima b significantly. Such outbursts could strip away the planet's atmosphere over time, making it difficult for the planet to retain the water necessary for life. The idea that Proxima b could harbor life depends on whether it has a thick enough atmosphere, and if that atmosphere is protected by a strong enough magnetic field to shield it from harmful radiation. The magnetic field of a planet plays a critical role in maintaining an atmosphere. On Earth, the magnetic field protects us from solar wind and cosmic rays, which would otherwise strip away the atmosphere. If Proxima b has a weak or non-existent magnetic field, it may struggle to protect any potential atmosphere from being gradually eroded by the intense radiation from its star. However, if Proxima b does possess a magnetic shield, or if it retains some form of protective atmosphere, the possibility of liquid water existing on its surface or underground becomes much more plausible. Another interesting feature of Proxima b is its tidal locking. This means that one side of the planet always faces its star, while the other remains in perpetual darkness. This phenomenon can lead to extreme temperature gradients between the day and night sides, which could affect any potential habitability. In theory, the region where day and night meet, known as the terminator, might be more temperate, offering a narrow zone where life could potentially flourish. However, the extreme contrast between the perpetually sunlit side and the eternally dark side could create a hostile environment, with wild fluctuations in temperature and potentially high levels of radiation on the day side. The proximity of Proxima b to its star also makes it likely to experience extreme tidal forces. These forces occur when the gravitational pull between the star and planet creates significant stress on the planet's structure. If Proxima b experiences substantial tidal flexing, this could lead to internal heating, possibly sustaining subsurface liquid water through geothermal energy. This would open up the possibility for life to exist beneath the planet's surface, shielded from the harsh radiation above. Such subsurface environments could resemble the deep-sea hydrothermal vents on Earth, where life thrives in extreme conditions without reliance on sunlight. Scientists have also speculated that Proxima b might have an atmosphere capable of supporting life, assuming it is able to retain it over long periods. Recent studies suggest that the planet might possess a thick atmosphere rich in carbon dioxide or other gases that could create a greenhouse effect, potentially raising the surface temperature to levels conducive to liquid water. However, this theory hinges on the planet's ability to protect this atmosphere from the harmful effects of Proxima Centauri's stellar flares. If Proxima b's atmosphere were to be stripped away, the surface temperature could plummet, making it an inhospitable environment for any form of life. The search for life on Proxima b will rely heavily on future missions and technological advancements. As of now, the planet remains an enigma, with only basic data available regarding its size, mass, and orbital period. More detailed studies are needed to understand its atmosphere, surface conditions, and any potential signs of habitability. Instruments like the James Webb Space Telescope, which is equipped to observe infrared radiation, will be pivotal in identifying key characteristics of the planet's atmosphere, such as the presence of water vapor, oxygen, or other biosignatures. Through these observations, scientists hope to uncover whether Proxima b's conditions could allow for life to emerge and survive in such a harsh environment. In conclusion, Proxima b offers an exciting opportunity for exploration and discovery, but significant challenges remain. Its proximity to its host star, the activity of Proxima Centauri, and the planet's tidally locked nature all pose questions about the planet's habitability. Nevertheless, as technology advances and our understanding of exoplanets improves, Proxima b remains a tantalizing target for the search for extraterrestrial life, helping to push the boundaries of human knowledge and our understanding of life in the universe. The next few decades of research could provide answers to some of the most profound questions about life beyond Earth.